we know that we can use Gaussian elimination to solve a linear system for its unknowns by adding multiples of one row to another row so that we can isolate variables and solve for those variables very easily simply by just dividing one number over. In this particular case, we would be adding -2 times the first row to the second row to isolate x2 when multiplying out the second row by the first column to get that x2 is pretty simply -1/3. But we know that we can solve these systems computationally. We saw that in the very first episode of this series. And we already know the back-end procedure of solving an upper triangular system such as this one. In the previous episode, we took a look at the forward and backward substitution algorithms, and at least for the upper triangular case, we saw that we could use the back substitution algorithm. But the question still remains, how do we solve a random AX equals B system that is not necessarily triangular with computational methods? And the aim of this video is to answer that question. Howdy folks, my name is Nick, and welcome to the fourth video in my series on computational linear algebra, where we are going to discuss structured Gaussian elimination. So how do we actually go about solving this AX equals B system right here? If it's not triangular, how do we develop such an algorithm or some sort of computational method, which realistically has to be some kind of algorithm, to find the solutions to this system? Well, wouldn't it be particularly convenient if we could just find a way to convert AX equals B into an upper triangular system where then we could use the back substitution algorithm? Well, we can do that with structured Gaussian elimination. Let's consider this 4x4 example here. If we wanted to convert this system to an upper triangular one, we would need to zero out each one of these boxed values. In this particular case, I'm going to refer to each one of these as spines. And, well, rather conveniently, we can zero out these different spines. The first spine, or the spine of the first column, the second spine, and the third spine of the third column can all be eliminated by adding multiples of different rows to other rows. But we just need to apply some structure. We just need to do Gaussian elimination in a very specific pattern that we can code into the computer so the computer knows that pattern and can use it to solve the system or convert this system to a upper triangular system every single time. And so how would we actually do that? Well, we do it one spine at a time, starting off with the first spine. There are 3 values here we need to get rid of. And so it'd be particularly convenient to eliminate half the values we need eliminated or zeroed out all in one go. And I want you to note that the first row doesn't need anything changed. We're not zeroing out any values of the first row, so it'd be particularly convenient for us to add multiples of the first row to the second, third, and fourth rows, since it's not changing. And so how do we do that? Well, we need to get multipliers, because we need to know what multiples of the first row we need to add to the second, third, and fourth rows. And we do that with this very simple formula here. We want to get rid of the first spine. The way that I like to think about it is that if, let's say, you're going to a chiropractor, they need to adjust one vertebrae at a time of your spine, and that's all we're doing here is we're just adjusting different values to make all zeroed out. And so we do that by dividing each one of these values by this first value in the A11 position, since that is what is going to be added to the rest of these. And in reality, we're adding a negative multiple for each one of these, so we're really doing subtraction here. So our first multiplier, L21, which conveniently by this notation is the multiplier for the position we are eliminating, is really simply just 4 divided by 2, which is equal to 2. So we're going to be adding -2 times the first row to the second row. Or really, we're subtracting 2 times the first row from the second row. Our second multiplier, L31, is the same exact thing. 4 divided 2, which is 2. So we're just going to clean this board up and say that that is also rather conveniently L31. We can also get L41 here really simply, which is just 6 divided by 2, which is just 3. I'll allow you right now to go through and do the arithmetic for this, since this is not an arithmetic course, to see that our system converts to this. Note that we still have 2 spines here, but the values of these spines have actually changed. But now we're going to focus on the second spine. The simplest way to think about this is that we're just working one column over at a time, or one spine over at a time. And so, are we going to use this first row here? Or are we going to use a different row? Well, it doesn't make a whole lot of sense to use the first row because we have this 2 right here. We've already zeroed out the first spine into all zeros, and so adding any non-zero multiple of the first row to the second, third, or fourth rows will result in a non-zero value being in a position on the first spine that we need to be 0. We've already adjusted this spine. It's already in the position that we need. So we move on from the first row. We're done working with the first row and we move on to the second row. Note that this second row has nothing that is changing any longer. So we use the next value on the diagonal as our key defining factor in getting the next multipliers. In this case, we're using A22. So you can see right here that L23 is going to be -6/7. And L24 is going to be 2/7. And you can see where this gets kind of nasty from an arithmetic standpoint kind of quickly. This is not something that I would want to do for a very large system, nor do I necessarily even want to do it for this particular system. So I'm not. The same sort of pattern happens with the third spine here. These values will end up being zeroed out. There will be no use to us using the second row, because if we add values of the second row to the third row or the fourth row, these values are not going to be zeroed out anymore. So very simply, for spine 3, you would just follow a similar sort of formula of LM3 is equal to AM3. That was a terrible 3 divided by A33. You're always going to be dividing by the diagonal values. If you're trying to cancel out the third spine, you're on the value A33. Fourth spine, A44. If we were doing this for a 100D system, if you're trying to cancel out the 98th position, you would be dividing by A98. Or A9898. That kind of just sounding a little bit weird there and kind of getting into the weeds of the notation. But this is not a pure linear algebra video series. This is not an arithmetic series. This is a computational linear algebra series. So let's get into the actual code. And we'll start off with Python. You can see that we are still using the cowboy linalg class we used from the previous episode, and we still have our solve utry function here, which is the back substitution algorithm. But you can see what I've done here is I have created a structured Gaussian elimination function, which is going to allow us to do structured Gaussian elimination. We are passing in an A matrix and a B vector, and you'll see, just like the back substitution algorithm, we are getting the dimensions of the matrix that is being passed in. The next thing that we're doing is we are creating a matrix of the same dimensions as our A matrix that is all zeros. And we're doing this to store our multipliers. And this is particularly nice and convenient because this will allow us to store the multipliers in the positions that multiplier is going to be canceling out. Then we are setting up a sort of double loop here in lines 19 and 20, where we are going to be able to take care of the indexing of the rows and the columns. Inside here, we are getting our multipliers very quickly and very easily, and you can see that this is going to give us a 2, 1, 3, 1, and 4, 1, and then so on and so forth. And this is just getting and storing our multipliers. Then we are taking our A matrix and subtracting off multiples of one row from all of the other rows. And we're doing the same thing in line 23 for the B vector. Remember that we have to apply structured Gaussian elimination to the entire system, not just the A matrix. So we're doing that to the B vector. And then what we're doing is we are returning that A matrix and B vector, which in reality is a upper triangular matrix and a C vector or a changed B vector. This all didn't fit on one screen, so here is the main function for what we're doing. We are generating a random 4x4 A matrix, and because we are going through and changing that A matrix into an upper triangular matrix, we have to save a copy if we want to check our work. Then we are generating a random 4D B vector. Then we are going ahead and we are putting our A matrix and B vector through structured Gaussian elimination. And then we are solving that converted system. And then you can see with the rest of these here, we are simply just outputting those to the terminal so we can see what they are. And then in lines 43 and 44, we are checking our solution. Per usual, all of this code is available on my GitHub and GitLab pages, linked in the description down below, and I will encourage you to go and clone this code or download it and begin to mess with it. A really fantastic exercise would just be to mess with some of the dimensions of these. Remember, we're only doing this for square matrices so far, but start messing with the code and seeing how it actually works. When we run this code in a terminal, you end up seeing our generated A matrix and our randomly generated B vector. Here is the upper triangular matrix and C vector from structured Gaussian elimination, and I want you to note a few things, mainly the spinal values. Note that all of these are not explicitly 0. And very similarly to what we saw in the first episode, since we are using floats as our D type, or particularly 64-bit floats as our D type, machine error is coming into play. And this is where we see that Python is a little bit more raw of a language than Octave. You will see this when we get into the Octave code. But these are all on order of 10 to the negative 15 or 14. And so they are incredibly tiny. If we were to round these or approximate these would be 0, and that would be perfectly fine. And so this is, for the time being, correct. We could really dive into the weeds of how to deal with computer error and things like that, but we're not going to for the time being. So here you can see is our solution through the back substitution algorithm, and when we check our solution, we end up seeing the 79, 79, 6, 6, 25, 25, and 15, and we end up getting back our B vector here. And so everything checks out exactly how it's supposed to, and it ends up working quite well. But now let's move on to the Octave code. It's always a good idea to learn and know how to do this in multiple different languages. Here again, just like in the Python code, you can see we have our back substitution algorithm. I just kind of copied and pasted from previously. And now we have another very similar function, which is the structured Gaussian elimination algorithm. You can see that it's going to return an A matrix and B vector, and that we're passing in our A matrix and B vector. Similarly to the Python code, the first thing we're doing is we're getting our dimensions, and then creating a matrix for us to store our multipliers, which is just a matrix of zeros that is the same size as our A matrix. Then we're setting up a similar double iteration process right here for our indexing. We are getting our multipliers and storing them in the in this L matrix that we created. Then we're adding, or rather subtracting, multiples of the previous rows to the rest of the rows to cancel out the spines. And then again, we need to change the B vector also, so we're doing the same thing to the B vector to change the system. Note that for those of you who are using MATLAB and just trying to alter some of this code, this is not going to work in MATLAB. MATLAB, in my experience, which is much more limited than my experience with Python or Octave, has really taught me that functions in MATLAB are a little bit weird, and having two functions in the same file tends to get a bit odd. I strongly suggest that you use Octave for this purpose. Octave is also open source and free for you to use, while MATLAB is proprietary and you have to pay for a license. But there's just my little rant on that, and I don't want to get into any more detail about that because I could rant forever about it. Similarly, we are generating a random B vector and A matrix. This time we're doing a 5-dimensional system. We are plugging it into our structured Gaussian elimination algorithm so that we can get out a U matrix and C vector. Then we're plugging that in to solve utri, and then we are checking our solution. In the terminal window, you can go ahead and see right away our random B vector, our random A matrix. You can see our converted upper triangular system, and this is the nice part about Octave is, and even MATLAB too, is that it's a little bit better about understanding that you're doing this for mathematical purposes. And so we end up seeing these zeros, which is much nicer. Here is our changed vector, and here is our solution. When we check that everything works out and compare with our B vector by doing AX, well, we end up getting B back: 78, 78, 59, 59, 53, 53, 99, 99, and 59s in both of those. So everything checks out. So now you know how to solve any square AX equals B system, and in reality, this will work to some regard. And although we're only considering a square system so far, you'll see this apply and be useful in a few other different cases. But in summary, how do we solve this AX equals B system? Well, we pass it into the structured Gaussian elimination algorithm, which converts it into an upper triangular system, which then we plug into the back substitution algorithm, which provides us our solution. I want to thank you all very much for watching, and if you have any questions, feel free to let me know in the comment section down below. If you liked this video and you'd like to see more, click around the channel to see more, and consider subscribing if you want to stay up to date with this computational linear algebra series or any of the other work that I end up doing, whether it is applied mathematics related, astronomy and astrophysics related, or even just some other fun, weird, interesting thing I plan on doing. Be sure to subscribe. Again, thank you very much for watching, and I hope to see you again next time.